Hi, hello. So today we will look at the second task of week number 70, and the task is about generating the gray code sequence. So you've got number n between 2 and 5. Write a script to generate n-bit gray code sequence. And what that is, actually, it's a sequence, a binary representation of numbers. But unlike traditional binary representation, this sequence is built in such a way so that when you go to the next number, you only change only one bit. So you see, for example, here, like one bit right, one bit right, and like here is only one bit flipped. As well as here, but for example, look at these two numbers in traditional binary code. So when we come from 3 to 4, we have 3 bits flipped, right? These bits flip to 0 and this bit was set, so there are 3 changes, while in the gray code representation there's only one change, so only the first bit was changed. So that's the idea behind this gray code. Right, so there's the 2-bit gray code example. This is how it looks like. So it's 1, 3, and 2, not 2 and 3. And to generate the 3-bit gray code, use the sequence for 2-bit gray code and follow the steps below. So okay, so this is the original sequence. Then you have these binary representations of these numbers, then you reverse it, so put the last element first, then you prefix it with zeros, so this 0 was added, then you do the same with the reversed, but you add 1, and then you just join those sequences to a single sequence, and you will get the 3-bit gray code sequence for the number of 3, right? And this is the result. Right, and here's the result for another for the next level. So okay, so before we'll look at the solutions, one note from me. The note is about so you definitely can use this algorithm to generate the sequence, but there's also a simple way. If you just will like move a single bit mask from the lowest bit left, right, and you will just make some bitwise operation with the current number, you will basically get the sequence already. So yeah, there are 2 ways, and I hope we will find such solutions as well. Right, so let's go to the list of solutions. Let's start with the last one in the list, Raku 2. Right, so what's there inside? So here we have, okay, so yeah, so the main function takes the number, and we have the sequence for the first sequence, like 1-bit sequence, right, 0 and 1, and then while we are reaching the number we want, what we are doing, so we are doing first, we reverse the current sequence, right, and we iterate over this reversed sequence, and we collect the sequence, we put it in the current, right, so we append to this array, right. Then there's length of the already updated sequence, so with a few more elements. Actually, yeah, it will be doubled, the number of elements. And then for the first half, so it's div is an integer division. So for the first half, what we do, we just prepend 0, and for the second half we prepend 1. Yeah, I wonder actually if it's possible to combine these, but probably not, because it will be just an if inside the loop, right? Maybe, yeah, okay, so yeah, I think this is the simplest solution, but definitely we can use map instead of explicit loops. We increment this, actually, yeah, so there's while, and then we increment the loop variable. Probably it's simpler to make it with 4, but nevertheless, and after that we parse base 2. So right, so every string that we work here inside this while loop is basically binary representation of the number. So here we want decimal numbers again, so we make a transformation back to the decimal world and we print these numbers, right? So looks like it is a working solution, I believe. Like it should work. Raku to Raku, right? So I believe we need number, right? Yes. So for number 4, right? Yes, right. 5, right. And another comment about, so for example, let's take it like number 3. So you see, so when you increase this number, the sequence definitely becomes longer, but the first elements are exactly the same as it was on the previous step. So for example, here we have these numbers 1, 3, 2, 6, 7, 5, 4 on the sequence of 3, and we see exactly the same sequence in 5-bit code and then 4-bit code. And if you look at the whole 4-bit sequence, you will see exactly the same numbers in the next step. So probably you can use this fact somehow, right, to optimize the solution, for example. Right, let's go next. Roger Bell West, and his solution is this. So there's a test, so we immediately test the number for the 4-bit sequence as it was in the description of the task, and the main function is doing what is it doing. So yeah, again, so we're taking the first two numbers in the, well, all the numbers in the 2-bit sequence, 0 and 1, and while no, it's not while, so if there is something to do, basically, right, then okay, so this is the other way of solving this task without all those reverse and joins of lists. It's using some binary representation, and let's see what it does. So basically this is the main thing, right? Okay, so we are making it in a loop, and we are mapping. Okay, so S is the either current sequence or the previous sequence. Obviously it's a previous sequence because we copy it here and we copy the sequence back to the original value. So this is the sequence on the previous step here. So we make it flat. I'm not sure why we need that, but nonetheless, so we reverse it and we map it with some push. So this map has some side effects. So if map is parallel, then this side effect can be working wrong because it pushes to some data, and if these blocks were called at different times, or for example in different threads or whatever, then it might be incorrect, but currently it works. And yeah, in one thread it definitely should work. And so let's see what this is. So this is the current number, right? $_ from here, and so this is the bitwise operation, bitwise OR, right? Plus indicates the bitwise nature of the next operator. And K, what is K? K is basically, it looks like it's a mask. We start with 1 bit in the position 0, right? And then we just multiply it by 2, which means actually that we move all the bits of the number 1 position left to higher bits, and there was only 1 bit, so yeah, right. So yeah, so this is doing this, and yeah, there are no other sequences involved, so we get the result directly, right? And we return this S, and then we can compare it. So okay, so let's run this solution. Roger Bell West Raku chat 2. Yes, this example works. Right, going up here, I hope to see an interesting solution here as well. So wow. Right, so let's find the beginning of this program. The beginning of the program is here in the main function. So there are 2 input values. One is just positional and another is named argument if you want to increase default maximum value, right? Then you create the class and bit gray code, right? You do not create the class, you create an object of this class, and then you call get gray code method, convert it to array, convert it to Raku representation. Well, potentially if you call .raku, it is also possible to call .perl6, but it's outdated definitely now. You will get something that potentially can be passed again by Raku itself, and we convert it to string, and print. Right, and this is a really useful trick. If you want to print some debug information, you can just print it into this std error channel stream. Okay, so let's see what's inside this class. Inside this class, there is this class nBitGrayCode. There's an attribute dot an integer n, right? And there are some methods. Okay, so there's build constructor, which is actually called when you create a new instance, and it has two parameters, right? Those n and the max, and we pass it here as named parameters. And yeah, there are some restrictions, and the only thing this constructor is doing is just setting the value of this. Notice this, well, yeah, probably, yeah, it's xxx, but actually we don't need this build, right? We could directly set the value of n inside this new call, right? It will be going straight to this attribute. But nevertheless, we can note that this second sigil, which is twiggle, is an exclamation mark, and here is the dot. This is a good practice to use exclamation mark when you're working with variables, well, with attributes of the class inside the method, so that Raku directly accesses the container rather than uses the generated getter or setters. Right, but that's a separate question. You really want to understand how it works. Right. So we built it, and then we called this gray, right? Get gray, yeah, right. Get gray code function. What it does, so it returns an array, right? Interesting. So you see, so there's another way of specifying the return type. By the way, it returns an array, right? And here we also convert it to an array. So I think this one is actually a bit redundant because it's already an array, right? Okay, so given so depending on the value in n, if this value is 2, if we're generating the 2-bit sequence, then we return sec2. What is sec2? Sec2 is the list basically for a sequence, the 2-bit sequence, right? Right. I just wonder why is it outside in the class. So basically it should be inside, somewhere inside the class, some constants inside the class, because they only belong to the class. Right, and the seq cache is this sequence, right? So you return immediately the pre-computed result if for a small number. If it's 3, test basic method return. Wow. Okay, so you're returning the first cache. Okay, so I believe cache will, right, so the 0th element of the cache is currently keeping the 2-bit sequence, right? And if it's 3, then we initialize the value for the first position of the cache, which corresponds to the 3-bit sequence, and we fill it with something computed here. So we are copying the, as I said, like the next level always contains all the elements from the previous level. So here we are, and then we do what we do. We reverse the previous sequence, then 4. I kind of understand what it means, but I cannot express it. Right, so it's, so yeah, basically we are generating here the 3-bit sequence, which is the copy of the 2-bit sequence plus reversed copy. So yeah, and for each, so so you see, so this kind of, you can read it as for each element from here, add 4, basically set the first bit, right? So here, okay, so yeah, here we prepend 0, if you remember it from the algorithm description. So we have to prepend 0 for the first half of the list, and we have to prepend 1 for the second half. Basically, this is this construct prepends bit 1 as a front character in these sequences, right? But we're just using it like as integers. Flat array, I think this is a bit kind of Okay, right. Right. What's next? Next, depths to defined. What is depths to define? Depths to define is a method that turns an int and it. Wow. So probably it gives us the size of the cache, right? So depth is 0, and we increment it until actually while this is true. Yeah, remember phrases like I love you not, and here we are. So defined dot not. So yeah, I believe we'll just get kind of some information about the size, because while defined not, what does it mean? So while there is no, right? While it's not defined, we increment this while it's not defined. And if we increment this, we actually decrement the index. We start with base index. Base index is okay, so I understand. So this 4 is the length of the 2-bit sequence, right? So base index is basically the length of the current sequence minus this, right? So we just kind of make a correction for this. Okay, so yeah, I don't want to understand like every bit of this, but my impression is that this function, this method, returns the length with some correction, because the first element, the 0th element, is actually corresponding to the 2-bit sequence, right, and it's 4, and the first cache element corresponds to the 3-bit sequence with its length of, what is it, 8, right? And something like that. Right. Yeah, and there's also a method myIndex, which, right, so because we skipped these 2, so this is already 2, 0 corresponds 2-bit sequence. Right. So, and then for in a loop, which is a C style loop, okay, we take some offset based off all those, so yeah, it's right, and we call the private method, right? So this exclamation marks means private, right? So instead of dot, you use exclamation mark self. Exclamation mark generates sequence from base, so you've got you pass two naming parameters, first and second, and the third name parameter is partial sequence, obviously, which is the offset. What is this? So it's kind of, I believe it's the last, right? If it's partial sequence and we are generating sequence from base, yeah, I don't know what these are, but okay, so generate sequence from base. So right, there's first, which is positive, there's second, which is optional. You split into half, right, and round it down. You create this empty. Remember, there was, so empty is a constant. It's a sleep object, right? If I am correct. And then, so yeah, your homework is to understand what sleep actually is, and how it's used, and what is it for. So for, okay, so now we have the Raku styled for, which loops from 0 up to, but not including this half size, and we are taking two elements, which is really nice feature in Raku, to take two elements from the range or a sequence or whatever in a single go, and we fail. Wow. When I look at this, it resembles some piece of grammar, Raku grammar, where we have a few alternatives, but actually it's not the case. Obviously, this is just flattening of this, right? Whatever we have here, sequence or sleep or list or range, right? So we have three pieces. We flatten each of these pieces and we make a single list out of them, right? So the first one is just first, or some previously computed sequence, which is kept in cache. Then the So this is the 2-bit sequence. This is obviously the rotated 2-bit sequence. We again we make the same trick as we did it where here, like 2 by 2 power 2, but this is like okay, already computed 4, so we prepend it with 1, we prepend it with 1. I wonder why do we need it here. No, this is the okay, so this is the previous, for example, this is the previously computed sequence in the previous step, and here we prepend part sequence. Okay, so it's probably 0, right? So we multiply it by 0 actually, and we add 0, and this one I believe is 1, so we can prepend 1. But actually no, because no, because if the sequence is like 3-bit sequence with 8 elements, we should add 8 new elements with 1s, right? Okay. Right. Then we return unless return unless defined. Return if not defined, and first plus 1 is second. Okay, so we reached some point where these indices meet. Okay, if we continue, then we generate the second. So we save what we just computed in the cache, right? And again, like flat, I think there are too many flattening happening here. Probably it's a bit redundant. Okay, and again for the second, yeah, so now we start working on the second half. So I wonder why so yeah, I don't quite understand how this works, but now, okay, now we are doing exactly the same, right, for the second part. So these pieces look very but basically it's the same, right, with the only exception that this first, this second, and part sec L, and actually neither L nor R. Alright, right. So these L and these R are the indices in the second half of the array, which is right. Okay. So we build this sequence in the cache. What do we return? We return nothing. Generate sequence, right? So yeah, inside this method we just update the cache, and after that we can just access the cache at the my index. I think, yeah, it's just the last position, right? My index, where is my index? Right, so it's base index plus 2, so this is the last position in the cache. Where is it? I lost it, right? And we take that, we return it as an array. Again, this function, this method returns an array. We again convert it to array, and right. Okay, Raku Raku Chapter. Right. So, and for number 4, right. Okay, but it looks like it is a working solution. I think it's a bit heavy, but right. Mohammed Anwar, right. Solution number 2. Here it is. What do we have here? We have here the main function, which takes named parameters, so -n equals 3, and we print some. So okay, so we print this length, and then the sequence. Maybe I should make it a standard comment. Instead of using printf, I think it's better to use string interpolation in Raku. So why like encoding output pieces with %? Right, but that's the matter of taste, I believe. And right, the main code. So we've got this hash with the first 2-bit sequence ready, and for sequences more than 3, with more than 3 bits, with more than 2 actually, yeah, right. So what we are doing, so we're taking the previous sequence, right? This is the previous sequence. We reverse it and flat it and make a new list. So for the second half, and then for the first half we prepend using map. Now this is a valid use of map with no side effects, and we prepend 1, right? And so basically, yeah, so we're working with bits as with strings, which is fine in Polish language, right? And then you merge those lists together to get a new level, and you save it in the, let's call it a cache again. So right, and after that, so you loop over the current level, right, and then you loop over the elements within this level binary, and you push to the result. What do you push? You push this decimal representation, which is just this. So you've got this, so in Raku you can type something like this, right? And it will get decimal representation of this number in this base. So this is what happens here. The only thing is that we're creating it as a string, and then we pass it and we take the integer out of it, right? And then you push, so you collect the elements in the result and return result. I think again, so there are too many flattening happening here and here and here and here and here, and probably this one can be done as a map, but why not do it like this, right? Okay, so let's run this. Raku right, 3-bit, and what about 4-bit? No, right, yes, okay, looks like a correct solution. Okay, Lauren, the solution is here. Okay, right, so no need to have 1 2 4 3 here. Why 1 2 4 3? What is it? So basically here is the here are the first two sequences, 0-bit, 1-bit, right? So, and in the main loop, in the main function, we can start at 1. So yeah, there's an input number with this whatever code check, and for so in loop we create the gray sequence. Actually we are using the function next gray, which I assume computes the next sequence based on all the previous sequences, right? Well, based actually on the previous. We don't need all the previous, we just need the previous one. So next gray, so int in format, build the format in string, right? So this is the way to convert it to binary, right? So we call format and then format and formatter. Oh wow. So it's fmt %b, then fmt %0, like 5. Okay, so yeah, we need, like, for example, for the 5-bit sequence we need 5 characters, and if the leading bits are zeros, we want them in the output. So this is like we generate this %0 5, for example, s, right? There will be zeros on the left side, and so we map this, and we map the elements of this. Again, flattening, so many flattening today. Then we make the reversed part, the second half, and we immediately prepend this one here. So we see there are 2 actions in one line, and for the first half we prepend 0. Actually, right. Then we join the lists, and we saw this today, we decoded back to decimal representation, right? So let's run it. Raku, Loren, Raku 2. Oops. Let's see a smaller output. So what that is? Okay, so Mm. Okay, so the first line prints us the wanted sequence, and the second line is just dump of all the sequences, right? Right. Okay, nice. Nice. Right, going up in the list, Javier, the alphabetical list actually. Right, so the main function immediately calls this gray code with default value, and this is a copy, so we're going to modify it. Why we are going to modify it? We are not calling it recursively, right? No. Ray code not found, actually. No, we are not calling it recursively. Right. Why do we need to modify this? Because here. Okay, so it's, but that's again the for loop instead of while and increment, and explicit increment or decrement of the count is not needed in Raku, right? Just while some sequence if you want to count down, just a sequence if you want to count up a range. Right. Okay, nevertheless, so we've got again this initial sequence, 2-bit sequence. Then we reverse it and save it in the separate variable. Then we make a couple of maps, really clean code, and then we join them together by using flat, right? So it will just make the result, and we continue until we reach the number we need. Right, and then we print it as a, okay, no, not yet. So then we, okay, so that's the second way of depassing the binary. So actually we saw 3 already. So remember the first one with the colon B, then in angle brackets the decimal representation, then pass dash base 2, and this is the third one. The third option is just preparing the 0b string and pass it as an integer, right? And again Perl, right? So it's not Raku, but Raku here Raku 2. We need nan, right? No, we don't. Right. Okay, so it works. Good. Going to the next solution by Jalda, Raku 2. Here it is. So yeah, multi. Why multi? We have only one copy of this function. Integer n, where n is this. Right. So now we don't have explicit bits. We have just decimal numbers, which is fine. And if we need something to do, then for higher order sequences, we do. Right. So we map string sprintf 0. Do you remember from your head what this star means? I don't. So probably that's the argument against using sprintf in Raku. But nonetheless, so it will do something with this, and then we reverse this sequence. So yeah, but basically out of this we will, I believe, get 0. No, I will not tell you what it will be. And actually, yeah, what is I minus 1? What is I? I is the current bit sequence, right? So it will be replaced with like 0.5 probably again, right? And this one, what is this one? Where will it be in the string? Yeah, right. Okay, so that's homework for you. Right, so then we reverse it, then we map by prepending this 0 and 1 and explicitly printing it as a binary string of binary representation, and then we push the second list to the end of the first one, and meanwhile we convert everything to an integer again. So here we have strings with binary representation, and here we have already an integer, actually a decimal integer, right? After that we can prepare the output with quotes outside, with brackets outside and comma separated list inside, right? Okay, Raku, right, Raku, second solution goes here. We need to specify the length, and length is 4, and this is, what is it, 5, right? I wonder what it's like, 7, right? So yeah, so 8 bit length. And who is generating this? Wow, actually I see. So bit length, here we have the comment for the n. Wow, I didn't know about that you can use this comment against the variable. So we see, so n, and this helper text is taken from the source code. Nice. Yeah, I think it's a thing that you can use. Okay, calling crane, Raku 2. Yes, please down, please down, load. Right, okay, so main bits were bits more than 1, so yeah, that's the length, and generate great code and print it without extra parentheses. So here's the function. So if bits is 1, so for one bit sequence, we immediately return these two pre-computed values, and otherwise I believe we will call this function again, right? Right, so it's a recursive function. So what it does for these bits, I believe these are the bits which will be pre-appended, right? So this is it, right? No. This is the bit, and where is it used? Right. So this is where we prepend either 0 or 1, and we do it as a string concatenation, right? So these are numbers, but this number is used in string concatenation, so it will be converted to string, and we can concat the strings without losing the leading 0 bits. Alright, so great code is actually the great code of the previous level mapped. Right, so again, some preparing the format string 0% 0 like 5b. So because we want leading zeros, and if we are working with the second half, then we reverse it, and if we are working with the first half, we do not reverse it. So we see, so why nice. So nice. So I would make it like a separate line, gc dot equals reverse if dollar underscore, right? I will type it. I think I would use this one as a separate line, and after that just do it like this, and we are this is the return value of the of this map, outer map, and then we flat. So there are 3 maps inside, 4 maps, 1 2 3 4, and the final map, again using this colon base syntax to, I believe, convert it back to the numbers, right? Right. So so Raku wow. So the number for the sequence, for the 8-bit sequence, right, it should contain 256 items. Here they are, and for the 4-bit sequence we have these numbers 16, right? Okay, going next, and next is Athanasius, Raku number 2. Here is the code, and so in the main function we expect values between 2 and 5. Again, notice the Unicode less or equals character. I really like it. I don't know how to type it easily on the keyboard. I just copy it from Google, and then we then we basically call the Greek code's binary function and map the result as this binary representation Greek code, and then we join it right, and print. So again, why printf, why not string interpolation? So okay, so the main function, so input, output, input is number of bits, output is an array of strings. Notice that this is an array of strings. And so if n is 1, then we return 1-bit sequence. What is 1-bit sequence? 1-bit sequence, I don't see it, but I believe it's defined somewhere, right? Yeah, here we are. So 1-bit sequence is this array of 2 strings, 0 and 1. And otherwise, if n is not 1, if it's more than 1, then we take the previous sequence, right, recursive call again, and right, and then we prepend 0 or prepend 1 to the reversed sequence. I really like these spaces here. It's really nice that you can use actually spaces here. Probably you will not follow this practice, but well, these lines look really cool. And then you append the second half to the first half, and here you are. Right, so how we use this? Raku, nice Raku chat 2. We need number, let's say 4 for 16 numbers in the output. Right, okay, going to the next solution Arne, and here it is. Right, so unit sub, so this is the body of the main function until the end of the file. So there's n, and there's some flags to print debug information. So the 2-bit sequence. For the rest, we generate 2-bit gray code sequence based on the current sequence, right? And we save it. So basically, we will increment. We will make this. We will grow this array for this level, right? And some debugging if we need it. And we just then print this in square brackets separated by comma. Right. By the way, notice. I want you to take a look at this. So this is a string in double quotes, right? Inside this string we have the code block in curly braces, which is a piece of Raku code, and inside this piece of Raku code we have another pair of double quotes. So you have double quotes within double quotes, and they are passed normally. So we will not, like the Raku compiler will not stop here at this second. So it's really interesting. Well, definitely, yeah, you don't have to use double quotes here, but nevertheless, the fact is that you can use code block with double quotes in it within a string double quoted. Okay, so the function for the given level. So it's a map, binary representation of the previous level, reverse, prepend 0, 1, combine these lists together, these arrays together, and flat them to make a single. So probably you can flat it here and put vertical bar here, or you can do it like this, right? Or you can actually, I think you can use some append methods, but yeah, so there are many things to do the same. And finally, you convert it back to decimal. And if we want debug information, then just print the steps, right? Raku, it's like for 3 and for 4 bits, right? Okay, that is good. Simon is here with this solution. We take n between 2 and 5, we convert it back, the sequence back to digits. So I think, right, so these gray beans returns us a list of strings with bits, and bits are characters 0 and 1. So nice and interesting solution. So there are 2 versions of gray beans function. For the input number 1, we give this, and all the rest is recursively calculating. Really nice. So this is so we are taking the previous solution and we just then reverse it, prepend ones, and for this first half we prepend zeros. Right, and then we join this. So this is another method of joining. Just explicitly list these parts, put them in square brackets, so you've got this, and you can return it. Right. Okay. Like say for 4. Good. Okay. A couple of more solutions. Shahid gives us this. Wow. Okay, so I have to run it from the interactive shell, and maybe gray sequence is, so this is a lazy sequence for all the numbers up to infinity. So I see, so there are 2 Unicode characters here. Well, all characters are Unicode, but this is outside of the SKI table. So this is a reduction operator with double quotes. What is it doing? Is it just double quotes? Is it like converting it to a string or what? Then we here. So here we have 2 parts. We map every something. What is it? Sorry. Yeah, it's not reduction. Wow, yeah, it was stupid. It's not reduction operator. It's just the sequence, right? The first element is empty, and then we have this. So we have the previous prepend 0, the previous prepend 1. Then we reverse this, and yeah, and we then join together. Okay, so say GS, for example, say the first few elements. Say gray sequence 5. Right. Okay, so this is only binary. Yeah, well, this is a valid solution, right? So you don't convert these strings back to decimal representation, but these are the bits, right? Let's see. So it's 0, 1, 3, 4, 0, 1, 3, 4, and yeah, 7, 6, was it 5 and 4? Right. We can just immediately see that every time you only flip a single bit. Okay, so yeah, a really interesting solution with the sequence. It generates the result which is different from what we saw earlier, but nevertheless the sequences are correct. Right. Okay, nice. Node Raku. Here we are. So right, so let's call it for the first 5 numbers, and if the number is 1, we return this 1-bit sequence. If not, then we gray code sequence recursively call it again. So we take the previous sequence, right, and we are using it here as reversed, and here as the left half, and then okay, so this is a bit different from what we saw. So what we're doing here is just instead of just setting the bit, we're just adding, for example, for the 3-bit sequence, we're adding 4. Yeah, this is exactly so that's the combination of the algorithms, right? So combination of the algorithm when we just have a 1-bit mask and move it to the left, and the second algorithm, the heavy algorithm with all those rotations and of the list. Right, interesting, really interesting. But let's maybe run it. Raku node. Do we need an input? No, we don't need any input number. 2. Right, good. I like this solution. And finally, not finally, Mark Anderson. Internet is slow today, but it's here. Right, so main with n, initial sequence for 2 bits, and all the others. So we have the first part, we have the second half, and I think this solution is the best out of other possible options. So you don't have those extra characters the vertical bar, I mean, or extra method calls .flat, for example. You can just append a list to array, append an array to another array, and that's it. So then you map it back to decimals and you print it as an array. I wonder what that is. So if you have it, let's run it. Wow, hey, nice, thank you. So using my solution. So yeah, basically, so this is who showed this. Okay, and it was from the book, I believe, right? Yeah, chapter 2, using Perl 6. Nice, thank you. I really like that it's used. Okay, and right, so Raku, let's yeah, so this is string concatenation, this is string concatenation. So yeah, this one is really nice. Right, so Mark Anderson, Raku, do we need input? Yes. 5, for example. Right, so exactly the same numbers. Good, okay. Next is Luca Ferrari. Main function takes the parameter, print some message. Right, so sequence 0 is 0, sequence 1 is 1, right? So this sequence, so it looks like you don't have to be confused. So this is not the number of bits, this is just the element, the index of the element in this sequence. And we append the reversed version of the same sequence, right? Then add 0 or 1 to the elements. Yeah, so this is, I already mentioned this, so basically this is in a single loop, you either add 0 or 1, and definitely you need this check always. So this is where does it start? So this is like if true, this is if false, and this is the condition, I believe, right? So if it's more than half, then we add 1. If it's less than half, then we add 0, right? To the sequence, and mirroring is so this is the length, right? So this is the index. Okay, and again pass base, right? Okay, Raku, Luca, Raku, chat 2, number 5, for example, right? Okay, and I believe that's it, and here's my solution. Okay, so yeah, this solution is actually using this algorithm of using mask. So for this input number, so if this number is 4, then we have 16 numbers in the output, right? So basically this is this says up to 16, and for that we so we map all those numbers from 0 to 15, including 15. We are mapping this with this. What is this? So it's plus bitwise. Did I say bitwise earlier? Yes, I did. So where it was plus vertical bar is yeah, right. So it's not bitwise OR, it's bitwise XOR, right? Exclusive OR. And so we take this number and we exclusive OR it with something. I don't know. Yeah. So basically, I just took it from Wikipedia. There was an algorithm there, and I made a one-liner solution from here. But nevertheless, so yeah, so it gives you number immediately, right, without calculating all the previous steps. Let me run it. Raku for the number of 5, for example. Right, so the same numbers as in other solutions. Okay, right, so that was the review of the Raku solutions of task 2 great code sequence from the Perl Weekly challenge week number 70.